just introducing Dr. Sung-Young Ho. He's the CTO and co-founder of CrossBar. He's been involved in a lot of their work in non-volatile memory technologies, ReRAM, and has received a number of technical awards, holds over 100 patents and 40 technical publications with tens of thousands of citations. And he got his doctorate from the University of Michigan. I'm going to go ahead and stop sharing. Joe, you can go ahead and start your presentation.
Sure. Thank you, Shay.
Well, we saw it briefly.
Yeah, I'm trying to save, yeah, full screen.
There we go.
Oh, yeah, okay, good. All right. Hi, everyone. I'm Sung-Young Jo from Cramium and also CrossBar. So today our presentation topic is a secure processing unit. Before we start, first let me introduce who we are. So Cramium is a minority subsidiary of CrossBar, and the CrossBar is a rigid memory technology, and the rigid memory is superior to flash memory in terms of scalability or reliability and security, and that we'll discuss that shortly. And we have rigid memory and production in 28 nanometer. And also we are working on currently with the customer in 12 nanometer implementing rigid memory. And we have more than 300 patents. And in fact, we were named as a top 20 semiconductor companies based on the portfolio strength by IEEE. So this is who we are. And so probably you have heard terms like distributed key management or decentralized computation or multi-party computation. These are very hot topic nowadays, since we are facing some issues in a traditional approach. Traditionally, our approach is more like single key based scheme, and it has been used in various applications, as you know, like managing digital assets or making transactions or digital certificate. However, this single key pair approach was more like a mainstream for when we do not have enough computing power or when there is a lack of efficient algorithm for distributed or decentralized computing. However, nowadays, we do have good amount of computing power, and also recently there is significant progress in like MPC or multi-party computation that area. So single key scheme is becoming very risky. And the discrete key management, DKM, with a threshold signature allow to use multiple devices or multiple parties to manage the digital assets or like security or succession of ownership. But despite the benefits such as protection against the single point of failure, problem we see is that there is not enough direct support from the semiconductor manufacturer. So we have to use just conventional device. This is a problem that we recognize, and this is what we exactly want to address. And that's the reason why the Cramium is formed to solve this challenge. So if you see some of the DKM or MPC protocols, for example, here I brought about 3 algorithms here, like GG18 or Lindell 17 or CGMP21. These are very popular MPC protocols. As you can see here, it's actively revised. And there are some papers that even revised more than like 20 times since its initial publication. So one requirement for this is that silicon or hardware support should be able to handle these rapidly evolving protocols. And in coming few slides, and actually I would like to show some limitation of software-only approach and using MPC as an example. So here I use CGMP21 or like a GG18, and GG18 is actually heavily used by those Binance exchange. So as an example here, so as you know, during the key generation phase, each device or member creates their own secret and collectively compute group public key, which will be used to verify group signature. Typically, the key generation phase requires multiple rounds. As you can see, rounds 1 through 5 or rounds 1 through 4. Normally, in each round, everyone computes and verifies data received from others And usually it takes about as little as maybe 3 rounds to as high as maybe 10 rounds. So although this library like CGMP21 or GG18, these MPC protocols can handle unlimited number of parties, however, in practice is normally limited to only a few parties. In this example, I show like 4 people here, so P0 through 3, so about 4 parties again for each case. Already even with these few members, already you can see key generation takes already several seconds, or it can be more than 10 seconds. So this is one of the reasons why software-only solution is not enough. So this is one of the challenge, adoption of distributed key management or multi-party computation. So in next slide, let's review since round 1, round 3, it takes a long time. So we wanted to see what's causing this long time. So you can see if you here, so round 1 breakdown is shown here, round 3 breakdown is shown here. As you can see, the failure key generation takes longest time. And by the failure key generation is important because in the blockchain application, elliptic curve DSA is covering more than 90% of blockchain. And unfortunately, there's a non-linear signature scheme. So we need a kind of homomorphic encryption scheme to make it work for multiple parties. So failure key is required. And at the same time, there are a lot of attack or proof is required. So that like zero knowledge proof step for failure takes quite a long time. So hardware need to cover this failure or homomorphic encryption, and the zero knowledge proof verification or computation need to be addressed in hardware. So signing phase is also similar. So we just discussed that the key generation part. Once key is generated, then multiple party members come together and jointly compute the group signature without revealing individuals' secrets. So that's what we do during the signing phase. Here I use the CGMP21. Again, this slide shows one of the big issue here. When 2 people, small party, yes, maybe reasonable. It only takes maybe about 2 to 3 seconds. Okay, depending on people, 2 to 3 seconds may be too long too. Well, when you expand just to 5 people, we are not talking about 10 people. So 5 devices, already over 10 seconds, which is not acceptable. So software-only solution is obviously not scalable in terms of MPC calculation. This is one of the issues. And this is in terms of like a multi-party computation, but also there is a bigger challenge or bigger issues we see. If it's a cold storage, actually there are more issues. So typical architecture for cold storage, for example, like Bitcoin wallet or those things, typical structures are like more likely this kind of architecture where you have the CPU and the memory and not necessarily secure CPU and not necessarily secure memory. And there is no enough physical countermeasure. And people just put secure element and call this system secure because we use a secure element. But real problem is that these are discrete components. So connection between two, the bus is exposed. So this is a heavy target for the attackers. And another issue is that due to the lack of semiconductor support, as I mentioned earlier, wallet vendors or manufacturer has to use off-the-shelf components. And what it means is that because you have to buy them off-the-shelf components, is expensive and not necessarily secure. And probably you guys are expert. Individual component may be secure, but putting together is not necessarily secure. So there's a problem for the off-the-shelf component. And furthermore, secure element is not really for modern blockchain applications or modern cryptographic applications. It only offers traditional and controversial actually primitives. As you know, like NIST curve, potentially all the NIST elliptic curves has backdoors. There's a debate here, but this is a big concern. And on top of that, is based on the unreliable memory. All the secure element virtually use so-called flash memory. We will discuss a little bit later. Is insecure. Inherently, it's not suitable for the secure application. And also it comes with a very little amount of memory. Normally secure element has maybe tens of kilobyte max. That's definitely not enough to store enough key, unless you have hundreds of secure elements, which is not practical for the application. And on top of that, this secure element approach is typically centralized security. What it means is that first to use it, we have to have a strict NDA, even that we do not know how the cryptographic functions are really works here. We have no clue. We just have a kind of black box approach. We just have to trust what vendor offers. So there is no visibility. We can never verify it. So that's why it's centralized security. So there's inherent problems. As you can see, even in this, I have not listed all the issues, but even here, you can see there are a lot of issues. So this is the issue that we recognize as a whole, and Cramium wanted to address this issue. So our approach is slightly different. So our approach is that instead of having all the discrete components, we want to have like a memory or CPU or secure storage or accelerator, all these components in the single chip monolithically integrated, instead of having the multiple components connected to by the open bus. We just combine all the things during the manufacturing in a single die, and all those chips are heavily protected by the physical countermeasures. That's what we are doing. And also, we do not use the flash, but we do use the secure memory, and which is more reliable and gives more performance. And we have a couple of slides showing why RDRAM is better in terms of security compared to flash memory. And the manufacturing itself is done in the leading foundry TSMC. And we are planning to produce this chip in 22 nanometer. So for your information, conventionally CQ element is manufactured at 130 nanometer all the way down to 40 nanometer. So 22 nanometers, a multiple generation ahead of any conventional CQ element you can buy in the market. And 22 nanometer or advanced node means it's smaller, therefore lower power consumption and higher performance and more secure. Because 22 nanometer means pitch, distance between the metal to metal, distance or logic to logic is much more dense. So it's very hard to reverse engineer, even it's a physical invasive attack. And also, as I mentioned earlier, architecture-wise, we combine all those elements, all these components in a single chip during the manufacturing. And the core-wise, and we are planning to offer ARM Core M7, or with a collaboration with Bunny, who is another presenter. So we're planning to also offer RISC-V. And we'll offer actually cryptographic primitives that are heavily used by blockchains. And more importantly, we will take open development approach. So open source and open hardware, that's our base approach, so that you can verify, you can see what we're actually doing. So that you don't have to trust us, you can just see and you can verify. That's our basic approach. So let's briefly review the crypto primitives that we plan to provide. By the way, this is non-exhaustive list, and we do have plans for various chips in near future, and each chip may have different configuration. This is just as an example. So as for the public key scheme, we do offer elliptic curve crypto, like including elliptic curve DSA, or Schnorr or Edward scheme on the SECD curve, which is heavily used by more than 90% of blockchain, and the Edward curve or Ristretto, and the NIST curve, and for the backward compatibility, we do offer RSA as well. And we offer a homomorphic encryption, failure crypto system, direct hardware acceleration. This is very critical for MPC. And hash-wise, Rife MD and the SHA family and the Blacks and Keka. All of these are heavily used by, again, emerging applications such as blockchain. Of course, AES for the encryption. And we do offer atomic level acceleration for zero knowledge proof, because zero knowledge proof is another area that consumes quite significant computing time, especially for modern application. So furthermore, we aim to achieve very flexible but secure chip. So to do that, we provide two operation mode. Here, MCU and the CQ element is a single chip and is protected by the physical countermeasure. So in mode 1, MCU just issues a command, and the state machine-based CQ element process all the protocol level without coordination from the MCU. It just execute all the protocol. And of course, the data is never revealed, even though the entire chip is heavily guarded and secure. But CQ element, for the additional layer of defense, the sensitive data is never exposed to the MCU. It stays only inside the CQ element, and only result will be sent back to MCU. So this is mode 1. And in mode 2, so shown on the right, is more useful when CQ element does not support full protocol acceleration itself, but only offers maybe atomic levels. By having this mode, MCU is coordinating multiple atomic level operations, so that you can create arbitrary protocols using these atomic level operations. Again, here, sensitive data is never exposed to the MCU. So this is very critical, because in modern application, there are new concept you wanted to verify, but if the CQ element doesn't support all the functionality, you can still have the means to coordinate by using atomic levels, yet still secure. That's how we try to achieve the flexibility while securing the entire process. This is our approach. And let's discuss a few slides comparing flash and the RAM and showing why this memory is important for security. So flash memory and the RRAM, the fundamental difference is the physical mechanism. Probably you guys well know, right? Flash memory is a charge-based. In other words, it stores electron to represent information 1 or 0. So depending on whether you have a lot of electrons stored in the device or not, it represents digital 1 or 0. However, for the resist memory case, we use the metal ions. Only we need a few atoms, not really hundreds, only literally few atoms. Basically, the resist memory consists of top electrode and the bottom electrode and the insulator in the middle. When the metal ions are connecting the top and bottom electrode, is conducting state. When there is no bridge between the top and bottom electrode, this is insulating state because insulator is in the middle. That's how we store the digital information 1 and 0. So difference between two is that, as you can guess, storing electron is extremely challenging. The reason is that, let's say we store the electrons in floating gate here. There are various mechanisms that electron will escape. For example, if there is a single defect, electron will hop to the defect and escape. Or there is ion, like a sodium ion, it just combines escape, or direct tunneling. Even for the very state-of-art verification, it's impossible to have ideal insulator. There is always some ionic contamination, or there is some defect, or there is inherent physical limitation like direct tunneling. So because of this reason, actually you lose a few electrons very easily within a few days. When the device is scaled down to maybe 20 nanometer or 28 nanometer, we literally store about 100 electrons. But problem is that one electron escape every day or two. So in other words, once you store the information after maybe 6 months, there is not much information left. So retention is gone. That is a reason why there is no flash memory below 28 nanometer. Even TSMC or Micron, they themselves like acknowledge that they don't see the flash is scaling down in beyond 28 nanometer. So that's why all the secure element or conventional chips are 40 nanometer up because there is no practical memory can work with the MCU in embedded way. That's a big problem. However, for the resist memory case, it's based on few atomic space, few atoms, so that it can scale down below like 20 nanometer. In fact, we are working already 12 nanometer. And that's not only the reliability is not only the reason, and resist memory is inherently secure against invasive attack and optical attacks. Let's briefly review the invasive attacks. So this is actual device fabricated in foundry, and this is a 28 nanometer. And this is like a resist memory, individual memory cell. We program this device into 10101, for example. And here's zoomed in image is shown on the right bottom here. Actually, we cannot see, even manufacturer itself, we cannot see which device is programmed 1, programmed 0, because information is stored by only few atoms. Even with the most advanced imaging technique, it is almost impossible to distinguish program the cell or unprogram the cell. So that's why resist memory is very, very effective against invasive attacks, and which is not the case for the flash and many other memory technology. And another popular attack against the memory is the optical attack. And a resist memory provides strong protection against optical attacks. So as you may know, in general, semiconductor chips, IC chips, fabrication starts with a silicon substrate. That's how normally people call just silicon. So silicon substrate, then we build the transistors on top, then we build the metal wires on top, and the finish of the chip. So this is a typical, for example, cross-section view of the IC chip. The problem here is that optical attack. Attacker on adversary can inject light from the top side of the wafer or bottom side wafer. If we inject from top side, the light will be deflected or deflected by the metal layers. You know that metal is so dense that the light cannot go through. However, that's not the case in silicon. Light, by tuning the wavelength of the light, you can easily penetrate through the silicon and you can see what's going on in the transistor level. What's the problem? Conventional memory, flash, SRAM, or ROM, OTP, all those are built on this layer. So if you use the advanced imaging technique, you can see through from the behind the chip. That's a big problem. And especially SRAM, it takes only a few minutes to get the contents of SRAM nowadays. So that is one biggest problem. And however, register memory is not the case. Register memory is a so-called back-end memory. What it means is that register memory is built along the metal lines, not on the wafer level. It's somewhere in the middle of the metal lines. So that if you inject the light from the back side or top side, it's heavily protected in both sides, so that you cannot really see what's going on in the register memory. Of course, someone can argue that they can grind off these metal layers. However, we do have a heavy guard against it. We put the mesh, active mesh here, and we have sensors. So if adversary trying to remove the metal layer, we detect it right away, and we erase the confidential information stored in the register memory. So register memory is very secure against the optical attacks. Besides the use of this inherently secure memory, we also implement various physical countermeasures throughout the entire chip. In general, some other conventional secure chip only protect certain core area. However, we expanded the approach. We just cover entire area of the chip so that it's much more effective and secure. And some examples of physical countermeasures are like against the physical attacks, such as a FIP, like a cross-section or proving. So we have active shield or secure layout. Also, we have the countermeasures against the fault injection, like a laser injection or glitching, like a voltage glitching. Those are heavily used for the MCU attack or like a secure element attack. We have the glue logic and the detectors everywhere so that we can detect if there's glitch, then we can detect, we can erase a cell or we block the glitch. And also we do have the heavy side channel countermeasures and also algorithm-wise or hardware-wise. So they're trying to do the constant time calculation is for the core area, constant time or constant power consumption. We have also various workaround even to make harder for adversaries to perform these side channel attacks. And also besides that, we do have some secure memory boot and secure stage boot and multi-signature scheme. And we do offer various kinds of TRNG. So since TRNG is very important, let us review briefly. So TRNG is also very critical, heavily used component for the various crypto primitives. We do offer multiple independence is important. We offer independent sources, and also we provide option if the client or user doesn't trust hardware generated entropy, they are free to use the external entropy of their choice. So we offer both options. And to demonstrate why having multiple independent entropies are important, we used NIST test to demonstrate it. So you can see like NIST SP822, these are one of the test suite can measure the quality of randomness. So we used the intentionally poor entropy source to demonstrate the mixing of them is very good. So we wanted to use that. So if you see on the left, this is an intentionally poor entropy source. Here, the star mark here means it's a failure. So these are all different kinds of quality check for the randomness. All fail because it's expected because this poor entropy source that by design we used it. However, if you mix all these independent entropy source, multiple of them, if you mix, actually we can achieve very high quality, it's passing all the entropy tests. So even with the poor entropy source, when you mix together, it can provide high quality as long as the entropy sources are independent. So that's why having multiple independent entropy sources is good, because there is no ideal entropy source. Always entropy source work within the limit, like a certain temperature range or certain environment impact, like radiation or something. So there is no ideal. So you don't have choice but to use multiple sources mixed together to complement each other. So that's why we use the multiple independent source and option to use external entropy source as well. So we briefly cover the issue of the MPC and the conventional approach and the SPU. So in summary, we aim to provide a flexible and programmable platform with a high computing power, so multiple powerful CPU, and we wanted to take open development approach. And we offer large memory copies of several megabytes compared to a few tens of kilobytes. And also we heavily implemented physical countermeasures. And this SPU will be ideal for conventional and emerging crypto applications. Thank you for listening. And do you have any questions or suggestions? Or we could discuss it maybe in a discussion session later.